In this video, we're going to talk about the alternating series test. Alright, so we haven't talked much about series that have negative terms that pop up in them in the last couple of sections, because when we applied the integral test or applied either of the comparison tests, we had to have series that were all positive terms. So we haven't talked about series that have some negatives in them as well. So we're going to start talking about that in this section. In particular, we're going to talk about a special type of series that has negative terms in them, and that's referred to as an alternating series. So if you've got terms that alternate from positive to negative, positive to negative, positive to negative consecutively, then that's an alternating series. So here's an example of an alternating series. We have the series from 0 to infinity of negative 1 to the n over n plus 1. So that would give you positive 1 minus a half plus a third minus a fourth and so on. Another one here, again, where the alternating part's being put in here by this negative 1 to the n power. That's typically what we'll see. We might see another example of something else that's doing some alternating. But we started at 1 in this case instead of starting at 0, so the first term will be a negative 5 halves. The second term will be a positive 10 over 5. So it's a 2, and so on. But this one's going negative, positive, negative, positive. Again, the alternating piece is the whole, it changes from positive to negative to positive to negative, and so on. This one's also an alternating series, and it's written a little bit differently because of the fact that we don't have a negative 1 to the end, but you might also see one of these where they throw in a trig function to oscillate back and forth between 1 and negative 1. Cosine of n pi does that, right? So this one will be a 1 if n is even and a negative 1 if n is odd. So that's why we get the alternating signs. All right. We're interested in when these alternating series converge. So let's suppose we have an alternating series. So this negative 1 to the n is representing the alternating part. If this is the alternating part, then we're going to require the b's to be all positive. We have two conditions in order to be able to use the alternating series test. The first one is that the terms have to decrease as n gets larger. And the second one is that the limit of the terms has to go to 0. If those two conditions are met, then the alternating series converges. Notice again, remember from the nth term test that we had before, it's not enough for the nth term to go to 0 to guarantee that we have a series converges. But for an alternating series, it's good enough if we have something that is decreasing and goes to 0, then it'll converge. So, rather than going through a formal proof of why this is true, this is kind of picture of what's going on. If we have something that's alternating and getting smaller, let's say it starts off positive, well, if we take B1, our sum's going to end up over here. This will be our first sum, our S1. Our S2 is going to go backward because the second term in the series will be negative. So our S2 will be that B1 minus B2. Our third partial sum will be S3, but it's going to be off to the right because B3 will be a positive value in this case. But notice that we don't go back farther to the right for our S3 because the B3 has to be no bigger than the B2, or decreasing. Okay? Likewise, when we get to B4, it'll be negative. We're going to go back, but not back as far as the B2 did. So our S4 will be here. B5 gives our S5 here, and so on. So what's happening is that both of these both of this sequence of partial sums, the ones for the even values of n and the ones for the odd values of n, are going to get closer and closer to this sum. So it's not a proof, it's not rigorous at all, but it gives you an idea of why this alternating series test must be true, because what we're doing is we'll end up zeroing in a value because the partial sums is going to zero in on it. We'll go a little bit bigger, then we'll go a little bit smaller, then we'll go a little bit bigger, then we'll go a little bit smaller, but it'll get closer and closer to what the actual value is for the sum. All right, so let's do an example here. Let's say we look at the series 1 to infinity of negative 1 to the n over square root of 3n plus 7. Let's let bn be 1 over square root of 3n plus 7. The the rest of the piece, right, the non-alternating part. Certainly as n gets bigger, the denominator gets bigger, so the terms get smaller. So b sub n is decreasing. Also, the top is 1 and n's going off to infinity, so the limit will turn out to be 0. So that's enough to tell us that the series must converge. That's how easy it is to use the alternating series test. All right, let's look at a little bit more complicated example. We want to determine if the series n equals 2 to infinity of negative 1 to the n plus 1 log n to the second power over 2 over n converges or diverges. Notice that this series starts at 2. We could have started it at 1, but that just makes the first term 0, so that's not very interesting. So this one starts at 2. We're going to use the alternating series test on this one, so let's let our b sub n be the non-alternating part again. We need to show that this is decreasing. Well, in the previous one, we were just able to make an argument to say, oh, by the way, the terms are getting bigger in the denominator, so the terms must be getting smaller. Okay. This one, we've got a little bit more work to do. So let's see if we can use our knowledge from Calc 1 to be able to do this. So let's let f of x be the function natural log of x quantity squared over x. To check whether or not this function decreases is just a matter of taking a derivative and seeing that it's negative. So let's differentiate. Top is a chain rule here, so that's where the 2 log x times 1 over x is coming from. Derivative of the bottom is just 1 over x squared. Let's see, the x's here cancel each other out. We can factor out a log x out of both terms. So we're left with log x times 2 minus log x over x squared. Now, remember that the values for n that we're plugging in here are 2 or bigger. So that's the only things that we're interested in for the x's are 2 or bigger. 2 or bigger, log x is positive. Certainly x squared is positive. So the only thing we have to worry about for sign is 2 to the 2 minus log x. Well, 2 minus log x will be actually equal to 0 when x is e squared. E squared is about 7.4, give or take. So this will be less than 0 when x is bigger than that value, which means that the function will be decreasing once x is bigger than e to the 7th. Well, if that function is decreasing, the terms of the sequence must be decreasing. So we can say that b sub n is decreasing at least by the time we hit n equal to 8. And that's okay. Most of our other tests, as long as it's eventually decreasing, we're okay. It doesn't have to decrease from the start. It just has to be eventually decreasing. All right, so let's see what the limit is now. Because not only is it enough to see that it's decreasing, we need to make sure that the limit is 0. This gives us a chance to review L'Hopital's rule. And I always abbreviate L'Hopital's rule using a little L'(h) when I use it. Both the numerator and the denominator are going to infinity, so L'Hopital's rule applies. Derivative of the top will be 2 times log n times 1 over n. Derivative of the bottom will just be 1. So when we simplify, we get 2 log n over n. Do L'Hopital's rule again. Top is 2 over n and bottom is 1 for our derivatives, and certainly that goes to 0. So again, since we've got the non-alternating part for the series, the terms decrease eventually and the limit is 0. That allows us to tell us that the series converges by the alternating series test. Let's do another one here. We've got the series n equals 0 to infinity of n squared cosine of n pi over 2n squared plus 1. This is an alternating series. By definition, it is an alternating series because the cosine n pi alternates between negative 1 and 1, and the n squared over 2n squared plus 1 is certainly always positive. However, we cannot apply the alternating series test. Even though this is an alternating series, the alternating series test does not apply. Okay? The reason why it doesn't apply, in particular, is because if I look at the limit of the terms without the alternating part, they do not go to 0. The limit of the terms is 1/2. So really what we have here is the nth term test. We've got terms that aren't going to 0. In particular, the even terms, the terms that arise from n being even, go to positive 1/2, and the odd terms will all go to negative 1/2. that means that the overall limit of the terms does not exist, and that means that the nth term test for divergence tells us the series has to diverge. So do not get caught in a trap of always using alternating series tests for all alternating series. It's just not the way to do it. Okay? In order to apply to the alternating series test, we need to make sure that we have decreasing terms that have a limit of 0. This does not. Another concern of ours for series is how good they approximate values that we're trying to find. We'll see that more pop up when we get to power series later on. But being able to estimate, and we saw part of that with the integral test, being able to estimate is important, making sure that you're estimating the sum of the series correct the sum of tolerance level. So for alternating series, it turns out that the absolute value of the remainder, if you stop your series, stop computing your value of your series at n, then the remainder is what's left from between the sum of the whole series and the partial sum that you computed. The remainder, absolute value of the remainder, has to be less than the first term that you leave off. Okay? So to see why this is true, our S here is going to be, the sum of the series is just the sum of the B1 minus B2 plus B3 and so on. Let's just assume that the sign on B sub n plus 1 is positive. Just makes the argument a little easier, but it's the identical argument anyway. Okay, so here's the sum. This part up to B sub n is S sub n. Now let's look at the rest of this piece. If I look at negative B sub n plus 2 plus B sub n plus 3, we know we have decreasing terms. That's the hypothesis of the alternating series test. This value has to be less than 0. This value has to be less than 0, and so on down the line. And again, that's because the sequence of terms decreases. So our R is equal to S minus S sub n. That's our definition of R sub n. It's certainly equal to the tail end of the series. But we just said that all the other pieces in the tail are all negative, besides that B sub n plus 1. So the remainder must be less than B sub n plus 1. We also said that the sign, let's just assume the sign out in front of it is positive. If it were negative, we would just have the absolute value and it would be the same argument. All right. So let's use this knowledge now to see if we can approximate a series. Let's say we're asked to approximate the series 2 to infinity of negative 1 to the n over 4 to the n log n to within 0.000, excuse me, part 001, 1,000th. It's easy to see that the sequence of terms without the alternating piece is certainly decreases and goes to 0, right? The denominator is getting bigger and bigger. So the fraction gets smaller and smaller, so it certainly goes to 0. So the series certainly converges. We want the remainder to be less than 0.001. We can be guaranteed that the remainder will be less than 0.001 if the first term that we leave off, the n plus first term, is less than 0.001. Rearranging that, we would need 4 to the n plus 1 natural log of n plus 1 to be greater than 1,000. There's not a lot we can do with that algebraically and help us get on an n. So let's just start plugging in some values for n and see what happens. Well, if you put in 3 for n, that gives you a 4 to the 4th log 4. That gives you 354.891. If you put in an n equal to 4, you get a 4 to the 5th log 5, which is about 1648. So that 1648 and change, if we reciprocated, that's certainly less than 1,000th. So I don't need to use, the n plus first term would be 5, right? That's the 5th term. We don't need this term. I can stop at 4 and be okay. So once I stop at 4, add those the second term, the third term, the 4th term together, and get 0.079 as the sum of our series. The reason why we stopped at 4 again, this 5 is representing n plus 1. Is the first term that we leave off. This would be the term that we would leave off, and it's less than when we do the reciprocal, that's less than 0.001, because it'd be less than 1 over 1,000. So that's why we don't need the 5th term. we can stop at the fourth term to get our series correct within 1,000th.